Hello, my name is Andrew Elias. I'm a Senior Security Architect here at Synopsys. Today, I'm going to talk about security, and the presentation title of my webinar today is Building Security into Your SoC with Hardware Secure Modules. So, just a reminder before we start the presentation, just to help us, if you can turn off your pop-up blockers on your browser, please, that would be helpful. So we're going to talk today about how to build a secure SoC with a hardware secure module with root of trust. Now, the understanding of security is uneven across different application spaces. Now, more specifically, what I mean are some application spaces understand it better than others. For example, in the last 25 plus years, the music, movie, and even TV industry went through enormous changes to adapt to the digital revolution. It all started with sharing content that they learned how to lock down by implementing very strategic practices. We can see the results of these practices such as digital rights management or DRM, high definition content protection or HTTP, and device hardening practices like smart cards for set-top boxes. This industry has matured, but it had many years to evolve its practice. Even with that, there are security vulnerabilities in today's multimedia applications. Nothing is 100% perfect. The one point they understand is that you cannot create secure solutions overnight. It needs to be designed in from the start and secure from the ground up. So the general theme of my webinar today will focus more on protecting your SoC using a hardware secure module. Now, I'll start by briefly discussing some of the threats. I'll cover the players who are motivated in mitigating or even eliminating these threats and just areas of protection. I'll then discuss trusted execution environments and how a hardware secure module can be used to enable a root of trust. We will then get into the specifics of securing your SoC using a hardware secure module, provide consideration points when selecting your hardware secure module, and then finally I'll introduce our product offering at Synopsys. I'll end the webinar with some final words, and then we'll enter our Q&A session. So let's begin with threats. Now, we know as of today, attacks are on the rise. Not only that the threats are growing, but their nature continues to evolve. Device manufacturers need to take them seriously. Otherwise, there could be serious negative impacts to their business. From a consumer standpoint, we can only hope the consequences are not life-threatening. Everyone is affected because almost everyone uses connected devices today, from phones to laptops to TVs to video cameras, cars, and many more. Take last year's attack on the Tesla car, for example. Researchers have reported going through the Wi-Fi connection of a Tesla S model and being able to communicate to the driving system. Now, on the slide to demonstrate this attack from points 1 through 4. They claim that they can remotely activate the vehicle's braking system as well as stopping the engine. The attack requires physical access to the car, at least initially. But once connected, they can control the car's infotainment system, which could connect to the CAN bus and have access to the various modules on that bus. Now, for those who don't know, the CAN bus, or the controller area network, is the communication backbone to that car. Tesla fixed the problem, as well as added more security to the system by addressing other vulnerable points, such as enforcing a code signing policy. This was done via software update over the air. But what is still to be determined is how much stronger did they really make their security perimeter. Different software to mask vulnerability of the previous software does not sound like a strong solution. It may mitigate or even eliminate the current attack vectors, but it does not stop other types of attacks. So if they're not using some form of secure environment to execute their security functions, then I question the security strength of their system. So in today's market, there are many industry segments driving the need for security in their applications. On this slide, I'm showing you 4 different industries that are demanding security. And we know this by the various standards that are being published and adopted. So let's start with the industrial. These require machines to work properly. So any downtime or changes will disrupt the flow and have a direct impact on production, quality, and revenue. In addition, security to ensure safety is also a critical aspect to this. Automotive. The use of more intelligent onboard computers is a new technology which obviously has a lot of promise. but has vulnerability if not addressed. Any attack or any tampering to the car may cause damage to the car, but most importantly, can potentially harm the passengers inside the car. Standards like the AVITA, SAO, which is ISO, are trying to help plug the security vulnerabilities in this area. As I mentioned in my opening, entertainment is an industry that historically has shown the need for security. Studio, record companies, artists want to protect illegal distribution of their content because it's affecting their bottom line. Therefore, they embrace technology like DRM, HTTP, DTCP/IP 2.0, because it helps lock down their product. And then other specifications like movie labs are helping to fill in the security hole by providing implementation standards. Now, these are serious liabilities involved if a product is not compliant with the security robustness as mandated in those specifications. The last industry on my list is healthcare. In my opinion, this is the most obvious industry requiring security, yet it still has to go a long way. Predictability, reliability, safety are all critical operating elements for companies developing these types of devices. Each one of these segments requires a strong security framework, and a hardware secure module in an SoC can accomplish this. So, how do you enable security in an SoC? Well, it starts by understanding how you'll protect the three stages of the device. So let's start with the power off stage. The image and data is at rest and in persistent storage, for example, like a flash device. Is it required for the image and or data to be confidential? If so, you'll need some form of encryption and decryption. Do you require a form of tamper protection if someone changes the information? Well, then consider a form of authentication. Can you ensure the information cannot be shared across different devices? Well, then you'll need a way to uniquely bind that data to that device. So from power off, we go to the power up stage. Now the image and data is being initialized and used to execute and program the SoC. Do you need to validate the image and data on the device? If so, you'll need some form of authentication. What about the identity of the device and being able to securely ensure it has the right one? Again, some form of authentication and other process can be used to validate this. What is your boot up sequence? How many stages? Can you trust the functions being called at each stage? So finally, we reach the last stage, which is the running operation stage. Once operational, you must continuously check for potential threats. This includes features such as secure communication, as well as securely monitoring the access points in the SoC. So when you're building a robust security solution, you need to take into consideration several emerging requirements. What are you trying to protect against? Is it your identity? For your application, it is critical for you to detect that your software has not been tampered with. Now, I would argue that it is critical from a safety standpoint. Should you constantly monitor the software running in the memory? Do you need to have support for in-field updates? If so, by what kind of mechanism? So as a manufacturer of an SoC, these are important questions about your application. There are security functions to service each one of these items, and I will cover some of them throughout this webinar. That said, the most important I will stress now and discuss later is flexibility and scalability. Now, attacks are what they are today, but they continue to evolve as more and more connected devices of various capabilities enter the market. Can your application be prepared for those future attacks, the ones we don't even know yet? So, in order to secure an SoC at different phases of operation, you need to be able to run your security functions in a secure enclave that is protected from the non-secure areas of the SoC. This is called a trusted execution environment, and I'll discuss how a hardware secure module can provide one implementation of it. First, let's start with a hardware root of trust. What is it? It's the foundation of security in your SoC, and for robust security, it must be hardware-based. The root of trust is secure by design, difficult to be tampered with, and must provide one or more security critical functions. Because of its inherent security, the root of trust can be trusted by higher levels in the system, and hence build a chain of trust from the SoC to the operating system, to the various applications, and then right up to the external communication. So now let's talk about a trusted execution environment, or as they call them, Ts. A T relies on a root of trust and provides a secure area of the SoC to guarantee code and data protection. In this isolated environment, you can keep secrets like key material away from the non-secure area. You can also execute critical functions like security functions that require integrity. This is a way to execute a trusted process. There must be communication between the secure side and non-secure side. This communication must be managed in some form to mitigate the risk of attacks. Applications like virtual wallets or online banking apps would most likely take advantage of this space, but using a T is the fundamental protection mechanism when implementing security features. Using a root of trust to enable a T is equally important as part of the chain of trust. So there are various ways to implement a T, but in today's webinar, we'll concentrate on a particular approach based on a hardware secure module. So these hardware secure modules, as you see in the diagram here, or the acronym HSM. Historically, when we think about them, we think about these large appliances or a server rack on a server rack or a PCIe card in a PC. But if you begin to think smaller, then you have a USB stick on HSM or even a trusted platform module or TPM. But begin to think even smaller and embedded. And what I'm suggesting is the HSM embedded inside the SoC. Now you have a closed, protected environment that is tightly coupled to the fabric of the SoC. And like an appliance HSM, the embedded HSM provides its own service by running its own software and dedicated hardware. These embedded HSMs can perform similar functions as their large counterparts. For example, they can run cryptographic operations and provide secure access to key material. They can also be certified against various standards such as FIPS 140-2 Level 4, Common Criteria, AL5+, and others. But let's take a deeper dive and talk about what can be inside a hardware secure module and what critical security functions they can perform. So what does a hardware secure module that is embedded into an SoC consist of? Well, at a high level, a hardware secure module provides security functions to an SoC and communication with other external entities. What defines a hardware secure module are four essential elements. One, it's protected by a hardware which typically runs with software inside. Two, you must provide a minimum of cryptographic functions. Now, these should be proven and well understood functions like an AES counter. Three, there must be some form of tamper protection, and the implementation will vary from vendor to vendor. And the last one, it must have a user interface that the host can interact with, whether it's through the host CPU and or a host controller toggling some GPUs. But at the heart of all of these are the security function it supports. So what are the fundamental components that make up a hardware secure module? So the initial diagram here, let's begin with the security perimeter. It's the box. This perimeter defines what you want to protect on the inside. Now implementations will vary between vendors. Inside the box we have our secure CPU and it runs the software or firmware in it. The enablement for most of the security features supported in a hardware secure module is defined by the software running on that CPU. The resources around the CPU will help facilitate the security and perform these functions. Runtime memory. So when you're running the software on the CPU, you need to protect the runtime data required by the software. This includes the stack, the heap, etc. This data, or this memory, will contain keys in plain text and other sensitive information. So it's critical to ensure the tight security around this block. Again, different vendors will choose different approaches to implement this type of protection. Tamper resistance is the next one. It's an essential feature for this product. So code from the outside needs to be validated prior to running it on the secure CPU. This can be implemented in many ways, including a dedicated ROM that can only be accessed by the hardware secure module. Now, this implementation doesn't scale very well, but it does ensure the integrity of the code. Cryptographic accelerators are the next block. Although most cryptographic functions can be supported in software, it typically requires more memory and runs slower compared to using hardware accelerators. With hardware cryptographic accelerators, the CPU can run at a slower clock speed and potentially reduce the overall runtime memory requirements without sacrificing performance. True random number generators, or TRNGs, which to be clear, is not a pseudo-random number generator or a PRNG. This component will always produce a high-level entropy required for various security functions. Secure access to this module is absolutely critical. So for example, many protocols require entropy to generate the ephemeral keys. These are the master and session keys for the protocol. If an attacker can interfere with the generation of the entropy data, it can essentially render the protocol useless. For example, it'll be always generating the same set of information for every session. Secure clock is another important feature for the applications that require an expiration time. This feature can only be effective if the hardware secure module has access to a clock that cannot be tampered with. For example, applications allowing a limited time access to some resource such as movie rentals. The last component here is persistent storage or secure storage. Now, secure access to persistent storage is critical for applications that requiring state knowledge. For example, anti-rollback feature for devices can only truly be secure if the hardware secure module has secure access to the non-volatile memory, or NVM. What is critical is that the information cannot be tampered with, but also the access to the information cannot be tampered with. The last two options here, and one's marked in asterisks, are optional, which means they may not be needed if the application does not require it. So here are some of the main security functions provided by a hardware secure module. Secure monitoring. This feature can be available during power-up and during the runtime operation of the SoC. It will ensure that the proper components of the SoC are functioning properly. For example, it can monitor host instruction code while the host CPU is executing it. An attacker trying to insert malicious instructions can be detected, and this action can cause a notification back to the SoC. Secure validation and authentication. This feature is responsible for ensuring the validity of the code and the data on the SoC. The evaluation of the integrity of the code and data can be done through an authentication scheme, such as an RSA or ECC signature check. Typically, you can expect this operation during the power-up or runtime stage. Storage protection. As we mentioned earlier, this feature can provide a way to take plain text data in the SoC and securely encrypt it and authenticate it. The authentication and encryption can use a device unique key, so it can also uniquely bind it to the devices as well. Secure communication. You can generate a secure channel between two endpoints. For example, you can use a TLS protocol to do so. The master and session keys, which are part of the protocol, are generated inside the hardware secure module, therefore providing protection from any on-chip attacks. So this is typically available only during the runtime stage of an SoC. The last feature that function I'm covering here is the key management. Now, this feature provides a generic way to manage and generate keys. It keeps the key material inside the hardware secure module and therefore protected. And typically, right out of reset, this feature can be available. So, how can an SoC interact with a hardware secure module? A hardware secure module can be at the heart of the security infrastructure for an SoC. The host can interact with the hardware secure module either through the host CPU and or through a host controller that can toggle the GPIOs. Both interfaces can be used, but their access provides a different security implication. For example, malicious code running on the host CPU can observe the messages going in and out of the hardware secure module, or an attacker can cause a host controller to wiggle the general purpose input pins in a manner that is not intended or expected. But what effect will this have on the hardware secure module? So ideally, when there is malicious code or actions inside the SoC, the best scenario is for the hardware secure module to detect the malicious event and provide a notification back to the SoC. So in the next 4 slides, we're going to review 3 important security features. They're going to include secure boot, secure update, and secure debug. So let's start with secure boot. The primary function is to validate the host code image by the means of authentication. And this is typically used during the power-up stage of the SoC. There are different ways to support this feature, and this slide presents one of them. So in this implementation, the secure boot feature requires a certificate that contains the public key that signs the system code. Both datasets are in external flash. Upon power up the SoC, the first block becomes active is the hardware secure module. And one of the first things it does is to begin reading the data at a known location. The hardware secure module will first validate the certificate using a root public key that exists inside its security perimeter. This root public key has been pre-programmed. Now, if the authentication succeeds, then it will extract the signing public key from the certificate. By the way, for anyone who's having issues seeing the slides or having issue viewing it, please refresh your browser to view, and you can download the slide deck as well. And you can also refresh using F5. I was about to get into explaining this process. So the first process is that it will start reading the system code from the flash. It will run an authentication over the entire image and notify the SoC if it passes or fails. Now, upon successful authentication, it will copy the data to the internal SRAM memory. Now, since the SRAM memory is inside the SoC, it's better protected from attackers and therefore somewhat safer to begin executing by the host. Now, we could take this a step further and support a secure boot verification structure for a multi-stage boot sequence. So instead of one certificate, you can have a certificate chain that will consist of a root certificate, one or more subordinate certificates, and an entity certificate. Now, without going into detail, each certificate represents an owner, where the certificate above, which is called the parent certificate, signs the certificate below. A chain of certificates is a representation of different owners. So in this example, the base certificate owns the base code and data. For example, these could be drivers for the different peripherals in your SoC. The base certificate signs the OS certificate, which allows the OS code to run on the SoC. The second security feature I want to talk about is secure update. Now, its role is to provision the remote updates provided by some external source. For example, this function is used for in-field updates. Now, there is always a threat or potential vulnerability when accepting information from the outside. You need to trust the source. Devices who do not properly provision the trust are always susceptible to attacks. So when considering a robust secure update feature in a hardware secure module, you'll need to consider all the points of the vulnerabilities. So let's start with the communication port. How can this port be accessed? Will it be over the air or will there be a direct connect? Whatever the definition is, the important element to look for is how this information gets to the hardware secure module. And another question to ask, what if there's an onboard attacker who can observe it or change it? So this is where a good protocol comes in. A good protocol will monitor the messages and provide a scheme that will ensure all the messages from each recipient was delivered correctly and intact, therefore eliminating any man-in-the-middle attack. The protocol to support the secure update should be based on identity, and we should also provide the ability to revoke any compromised identities. You may also consider adding a secure channel. Now, this channel can be used to transmit data either bidirectionally or in a single direction. The protected channel should support encryption and authentication to ensure that the intended packet transmitted was received properly. On the flip side, if we talk about a technician in the field with a direct connect, as I mentioned earlier, well, then maybe a secure channel may become less important since the protocol already confirmed the identity of the individual. That might be good enough based on the type of application you have. But here are some additional considerations when using secure update. Where to place the incoming data to avoid attacks such as rollbacks, because an attacker will use any opportunity to interfere with the process. Make sure the integrity of the data flow from receiving the data to where the final image needs to be at rest is safe and protected. On-chip attackers can swap this information, continue with the old information, for example. The last feature that I want to talk to you today about is secure debug. Now, its purpose is to put the SoC in a debug state, a vulnerable state for anyone wanting to control and or acquire the information from the SoC. Therefore, it's important to enable this state in a secure way. Now, there are two elements that are required to safely enable the debug mode. Authentication is the first one. This is important because it answers the who and the what. Now, this can be as simple to a complicated protocol, but it really depends on the need of the application. And integrity. The authentication is only useful if you can guarantee that the attacker cannot manipulate the results of the authentication scheme. Today, most vendors, like secure JTAG enabling feature, for example, use a simple approach, which is a shared static secret on both sides. The secret is typically burned into the SoC, therefore if the secret is ever revealed, it compromises the chip or, worst case, compromises the family of chips that share the same secret. This implementation has a weak security, but the overall cost is incredibly low. When using a hardware secure module, the secure CPU allows for more sophisticated authentication schemes. These authentication schemes can use a proprietary or standard protocol like TLS. Like secure update, you also need to consider the communication platform. Now, as a vendor of a hardware secure module, this is an important point to consider. Different communication platforms have different cost meanings for different customers. JTAG, for example, can be challenging if a customer must implement a protocol over this line. Not to say it can't be done, but the resources to do so are not readily available compared to using, let's say, a UART channel. So on the flip side, there are more security challenges around the UART communication because it is so readily available. But you can address this through a well-formed communication protocol. So the last important point of consideration before I leave this security feature is to be able to determine when to understand how to turn on your secure debug and to also understand how to turn it off. Some customers prefer to power cycle the device to disable it, while others will use some other means. But either way, it's important that the customer reviews this and understands the process to ensure that there are no security holes, because the last thing you want to do is accidentally leave the system in debug state. So when looking for a hardware secure module, you need to determine if it will meet all the requirements for your application. To do this, you'll need to consider the following four pieces. What are your performance objectives? What the flexibility and the scalability for your applications? What is your security risk profile? And what is your product cost? But as equally important, what is the ownership cost of your product? So let's start with the performance objectives. If your application operates in an environment where there are hard timing requirements for the system, then it's important to make sure the hardware secure module can meet those performance requirements. For example, automotive applications are asking for system boot up time but not exceeding a specific time value. This will have a direct impact on the performance of your secure boot feature, which will involve the type of cryptographic function, the size of the key that you'd like to use, and the size of the data that you need to validate. Where the type of cryptographic function and larger key size helps strengthen security, it comes at a higher processing cost. Just to give an example, you need more resources to process a 3072-bit RSA versus a 2048-bit RSA. Other elements that you need to consider that will impact your performance include memory latency, bus performance, etc. Flexibility and scalability is another important consideration in your choice of selecting a hardware secure module. Most of these vendors typically lock down the resource upon purchase because of the protective nature of the product. So incorrectly forecasting the resource needs for your product lifecycle may mean that you may not be able to scale your application in a way that you need to. This includes the ability to scale up the current security operations, for example, use a larger key set, or even add new security features. So worst case, this limitation can prevent your in-field applications from supporting changes to a specification. It's always good to have some degree of future proofing, as you may never know your customer needs or even your customer's customer needs. So when considering a hardware secure module, review your functions and understand what those upper limits of those functions can be. Understand what kind of expansion do you need when it comes to cryptographic support. Also understand what kind of product lifecycle do you expect your SoC to go through. So based on your application, what is your security risk profile? As a vendor of an SoC, do you fully understand all the vulnerable points in your system? Using a hardware secure module will help secure the implementation of these security features, but it may not close all the possible holes. An attacker may never observe the key or even manipulate the protocol flow, but it can potentially use the action to still get the thing it wants. For example, attacking a content protection protocol on a receiver. Allow it to fully authenticate with an upstream device. Once authenticated, it will begin to receive the protected content and place the unprotected content into a frame buffer. Now the attacker has access to the frame buffer memory and therefore now can steal the content. So knowing the type of risk is important as it applies directly to the customer of the SoC and the context they plan to use it in. A vendor of a hardware secure module should be able to explain how to securely interface these features and provide guidance on ensuring the data path remains secure even after completing the security features. A vendor of the SoC may not know the consequence that their exposure has on its customer's application. That's why it's important to document the risk so that the customer can properly evaluate the risk level in their use case model. So the fourth and last important consideration is cost, and this actually splits into two. You got product cost and you got ownership cost. So let's start with the product cost. You can always factor in the cost when deciding the strength of your security in your SoC. Some approaches to deciding the cost is prioritizing the vulnerabilities by using a weighting scheme. So for example, the vendor of an SoC may use a set of security features from a hardware secure module to support critical functions like secure boot, but they may not be too concerned when it comes to ephemeral key protection during a protocol session. Personally, I don't necessarily agree with that practice, but the cost consideration for doing this can be significantly less than trying to protect it. So adjusting your cost based on your security strength is fine as long as you understand the exposure level and therefore understand the consequences of that exposure level. Just to give you another example, some attacks require expensive equipment and in-depth technical knowledge of the device. These factors reduce the likelihood of an attack since only a limited set of individuals have access to this resource. The vendor necessarily may deem this to be okay if that is the case. But where it really becomes embarrassing for a vendor is when the exposure is easy and anyone at any age group can break it. The other side of cost that also needs to be considered is the ownership cost. So as a vendor of the SoC, it's always important to consider the additional cost passed on to your customer to support the security feature in your product. For example, the manufacturing flow and how will your security feature impact it. So as a vendor of the hardware secure module, this becomes challenging when the application wants to use a device unique key for certain applications. These unique keys have a big impact on the manufacturing floor because it requires the insertion of unique key material per device, similar to a serial number. So the challenge becomes now, how do you provision them on a chip-by-chip basis? Who on the floor has access to these keys, and how do you prevent leaks? It's an additional cost that they'll need to consider when supporting this. Other items that need consideration include when a customer wants to use their HSM. This is the one that they store their information in. How can you protect and integrate that flow? Will their certificate authority or CA require tools from you? And if so, how do you pass that sensitive information, like key material, from the CA to the person responsible for integrating the hardware security IP? All these flows need to be addressed in some manner. So the type of host application is another variable that needs to be considered. So a host application that is portable across different platforms is more ideal. It can handle 8-bit, 16-bit, 32-bit. But then you have to ask yourself, does it require a minimum performance to run on? Does it port well to bare metal systems, or does it run better on standard operating systems? Because the hardware secure module is inside the SoC, you also need to consider the interfacing with these signals. This can be achieved through good documentation, expected signaling response, and notification states that are important items that need to be understood. So I briefly described threat models. I provided an overview of the industry drivers as well as covered some basic requirements. I explained what a T is and how it can be enabled with a hardware secure module with root of trust. At a high level, I covered what a hardware secure module can be and from some of the security functions it can provide. We also covered some considerations for your SoC when selecting a hardware secure module. Now, I'd like to talk about what we have at Synopsys, because we have built a family of compact and high-performance hardware security modules with root of trust, and I'd like to cover one of them in particular, called the tRoot H5. This is our highest performance hardware secure module with a distinct architecture to provide a very high level of flexibility and scalability in order to satisfy your SoC's device lifecycle needs for today and for tomorrow. It is the highest performance because it uses hardware acceleration that offers 100 times performance boost for specific operations compared to its software counterpart. Now, this was intended to help you meet some of the strictest security and timing requirements. Now, I'm referring to the large cryptographic operations and processing of large payloads, and this is provided in many of the new standards. For example, fast boot up time. But as covered in the presentation, the tRoot H5 does support the multi-stage secure boot, secure update, and secure debug. In addition, we offer key management support, which uses the PK-Sysweb interface to help manage both the static and ephemeral keys. But I'd like to say this is not your typical hardware IP. The software component is a big part of this overall product. This product can be broken down to three main components. A hardware RTL component that must be integrated into your SoC, but unlike other security IPs which can be tricky to integrate, for example, accidentally exposing the secure memory to the non-secure side, our IP is different. We architect it in such a way that the integration steps are easy and straightforward. This helps build confidence in your design without having to be an expert in the security definition. The software is the second component and comprises of a firmware and the host software. The host software is designed to be portable across most platforms, and the firmware is easy to install and use. The third tRoot component is provided by a set of tools. Each tool is designed for a specific purpose. For example, one tool helps build the firmware while the other tools are used for specific applications. In one case, you can use the other tool to program your root key for secure debug. But tRoot's architecture is flexible and accommodates many use cases for the many manufacturing flow because we know each customer flow is different. Therefore, depending on your specific flow, we have documentation and support that provides guidance on how best to use our IP for your flow. tRoot H5 is designed to offer high-grade security solutions to help eliminate the many potential threats to your SoC. For example, malicious host software can be eliminated by using the secure boot functionality provided by a tRoot H5. In this particular case, you can even use the ROMless feature to enable secure boot. tRoot H5 will verify the image prior to running it on the CPU. Keys that are generated or stored in tRoot H5 are protected and remain confidential to the rest of the system. The tRoot H5 even supports loading a secure key port, which can be read by an external processor to decrypt and encrypt packets. This will protect against attacks that are trying to get access to the key material. So even decapping the SoC will prevent an attacker from getting at the tRoot keys. tRoot H5 uses a combination of key material as well as a key derivation function or KDF to generate the final keys that are used in the protection of the system. So just knowing the static material is not enough. This means that the attacker has to do a lot more to try to break the system. We offer fault injection resistance. This is becoming more and more important in a lot of systems that require integrity in their system. For tRoot H5, we offer runtime protection for our data and our instruction path. tRoot H5 will also protect the data that is pushed to the non-secure part of the memory. It will be encrypted and authenticated, which makes it tamper-proof. So any detection of changes will generate an exception in tRoot H5, which will notify the host. And at that point, the host can take some action. Side channel protection is another capability that tRoot can support as an advanced feature. Now, this is becoming increasingly important for various applications. Some examples include protecting against stealing keys by observing power signatures. So why tRoot Hardware Secure module? Well, first, it's secure by design. It offers the protection of the identity that is very difficult to attack. It provides strong tamper protection. It performs runtime integrity assurance. It has a secure key programming to external port, which makes it ideal for packet processing features, for example, like a TLS application. And it offers functions that can perform an overall security lifecycle management service for your system. It requires no ROM or dedicated secure external memory. This will help reduce the overall cost and engineering effort for your silicon. It provides increased performance for cryptographic operations as well as secure DMA. This helps in areas such as fast boot time or large data images, meaning very tight protocol timeouts while using large key sets on asymmetric ciphers, and plenty of more advantages to it. And as mentioned earlier, by design, tRoot provides a highly scalable and flexible security solution for your system. Two examples include you can expand the feature for down the road updates. You can change the size of the runtime memory. And that brings me to the end of this presentation. So to conclude, the security threats are evolving and the SoCs need to be ready. A hardware secure module can offer a strong security perimeter, providing the confidentiality and the integrity for those security functions. When choosing the type of HSM for your SoC, you must understand the security requirements you need. This includes the risk, the performance, the flexibility, and the cost considerations. At Synopsys, we offer such protection with the tRoot family of products. On top of offering a very strong security perimeter, its unique architecture offers a form of scalability and flexibility that is designed to work in many SoC environments. It provides a very rich and dynamic set of security features that will help you protect your system. Thank you today for listening to the presentation. Now, before we begin with today's Q&A, I am told to ask you guys to please fill out the feedback form that's opened up on your computer. To complete this form, click the Submit button. You can click on the red survey icon at the bottom of your screen. Either way, we appreciate you giving your feedback, and thank you in advance. Now, we're going to move on to our question and answer section of the presentation. And to participate in the Q&A session, just type your question into the Q&A box. Click the Submit button, and I'll try to answer as many questions as possible in the time that we have left. If I do not get your question to your question today, someone will get back to you through email. And thank you. One question that came in is to ask, some gateway devices contain a TPM. What is the main difference between a TPM and a hardware secure module? So a TPM, which is a trusted platform module, is a separate chip, whereas a hardware secure module like tRoot is integrated into the chip. Both supply similar functions, but a tRoot provides lower overall system cost and the potential to provide extra protection due to its tight integration into the chip. The next question coming in, should every SoC have an embedded HSM like tRoot? Well, the answer to this question can be very specific. So an embedded HSM with a tRoot, root of trust, cost area, and requires some software integration in the system to take advantage of this. So in some cases, it does make it a little bit too costly. So in very small devices, which only have a very infrequent need for this service, it becomes a bit of a cost for them. But in larger devices like gateways, hubs, or SoCs, or even industrial controller applications, the added area can actually reduce the overall system costs, power consumption, complexity, while greatly increasing security. which makes it much more economical. The next question is, where does tRoot store the keys? Is it out of the host CPU address space? There's a special port on tRoot where the keys that protect, that actually generate the security perimeter around tRoot is connected. It's the only port that we ask our customers to manage, to have good security around that port. But once you set the keys there and establish them, then the security perimeter at that point is activated, and then you can be able to see, with confidence, run all your security applications. The next question is, why did you select the PKCS11 as the common crypto API software interface? Why not Global Platform T? Well, Global Platform APIs came from the smart card background, and that has been transitioned to mobile devices supporting technology like Trust Zone. PKCS11 has similar features, but it's more general and it covers a wider market, and that's the reason why we chose it. The next question, could you elaborate on how unique identity of tRoot is implemented? Unique identity of tRoot can be implemented through what we call the device unique key, or I don't think I've used the acronym in the presentation, or DUK, D-U-K, not D-U-C-K. With a device unique key that can be provisioned uniquely on each device, tRoot uses a KDF function that then the firmware inside can read and establish that as a unique identifier. Now, when you start using applications like a secure storage application or a key management application, it can then take that unique identifier and start using it to, in the case of key management, it can generate more unique keys, static unique keys that the applications may need. The advantage of that, in that example for key management, is if someone ever decaps a chip and tries to look for those static unique keys that are always being used on startup when there's power in tRoot, they'll never find them, because not only do they go through a hardware KDF, it actually goes through another software KDF to generate those keys, and then they get finally used. So it's another advantage of having that. I hope that answered your question. What security standards do you follow for the tRNG module? The security standards we follow for the tRNG module, now I'm not the one who particularly works on them, so we'll definitely get someone to get back to you, but the main ones that I'm aware of are the NIST SP890 standard, 90C standard in particular. Again, unfortunately, I'm not the expert in the tRNG specification, so if you want a more thorough answer, we can provide it later. Is there a document for the HSM user interface? Yes, there is. The document can be available through our sales channel or through just contacting us through email, and we can provide it to you. Oh, a lot of questions. All right. Can the manufacturing provision software be made available as a private appliance, not hosted by Synopsys? It can be. It can be. It all really depends on the use case of the customer. And our experience with different customers who have different manufacturing flows, it really is unique. And it's really challenging to make sure that that the IP, the security IP that we provide, for example, fits in their flow. Now, we have a lot of experience with many customers doing many different flows, and we believe we have an architect, we've architected a design for the hardware secure or the tRoot module that will help facilitate and make it easy to adjust, to add to many of the customers' flow. But I guess, I'm not sure if I'm answering your question directly, but I believe the answer could be yes, it can be. Okay, I just got notice that we hit the time limit. So it looks like I'm not able to answer the rest of the questions. Any questions that are remaining, we will get back to you via email. For more information related to today's webinar, you can visit any of the resource links available in the green paper icon at the bottom of the screen. A link to the on-demand version of the webinar will be emailed to you in the next day or so. Again, I'd like to thank you all for joining me today, and I hope you have a great day.